Great. Thanks for having me. My name is Shumo Chu. I'm the co-founder of NEBRA Labs. And today I'm going to tell you how we are building proof singularity. So this is the outline of the talk. First, roughly the three-fourths, I will talk about NEBRA UPA, which is the first universal proof aggregator living on testnet today. And the next, I will talk about NEBRA OS, which is we're building these native composabilities of rollups. It's a new rollup stacks using NEBRA UPA. First, let's talk about the product we're having on testnet today, NEBRA UPA. So I hope everyone should read Dimitri's article about verifiable computation, right? I think he did a good enough job. I don't have to motivate people here, like why we need proofs, right? I think proof is a way to go. And the problem here is that the verification cost is one of the biggest remaining problems. And you can see this is a list of the verification costs we have today for Gross 16. Assuming we have 20 GWay and the Ethereum price is about 3,000, then we roughly about $22.5 US per proof verified on Ethereum. And for Halo 2 KZG, it's about $36 US verified on Ethereum. And for Stark, it's a hopping more than $100. So this is what Vitalik used to say, hey, do I want to pay $20 to add privacy to my transactions to buy a coffee? Probably not, because the coffee probably not worse than $20. And this is clearly a problem, and the NEBRA UPA is our attempt to solve the problem. So from the high level, how can we make ZK cheaper on chain? And the short answer is using ZK, right? Because the whole point of ZK is have this a verifiable computation, and trustlessly can verify things. We can using ZK to verify ZK in the sense that we're using recursive snarks to aggregate multiple proofs into a single proof, and then you get cost amortization of proof verification. So this is a very high level ideas of NEBRA UPA. So you can see there are several keywords here. First, it's universal, which means we NEBRA UPA support proofs from different circuit. For example, one proof can come from ZK EVM, one proof can come from Ishmael's ZK coprocessors, and one proof can come from ZK TLS, right? It doesn't really matter. Because of the universality, we're kind of pooling all the proofs and then using NEBRA UPA to generate the aggregated proof. And the aggregated proof is a single statement. Basically, the proof verification result of the proof 1, proof 2 to the proof n, all true, right? By this way, you only need to verify the aggregated proof on chain, then all the proof is verified. So let's take a step closer, right? So this NEBRA UPA is an on-chain protocol. So we have a NEBRA UPA on-chain contract, and this on-chain contract can be deployed to L1 and L2. And then once NEBRA UPA received your proof submitted, there is a coordinator off-chain, and the coordinator will spawn a network of provers to generate the aggregated proof, right? That's still a very high-level picture of how the NEBRA works. And these are the three properties we want to ensure NEBRA to have so that you don't get any kind of trade-offs when you verify a proof on NEBRA compared with verify a proof on Ethereum. So first is permissionless, which means first and foremost, so NEBRA's interface is just a smart contract. When you use NEBRA, it's just the same as submit your proof to Ethereum. So it's permissionless. And also it's a censorship resistance. So we have a very similar mechanism to comparable to L2s so that you can force inclusion even NEBRA doesn't work, if even we want to censor your proof. Basically, censorship becomes kind of impossible. And last but not least, it's kind of a progressively decentralizable, which means today we're running a network of provers. It's a distributed system, but in the future, we can decentralize that. So that's a high-level idea of NEBRA protocol. And using NEBRA UPA is extremely simple. So on the left-hand side, so I show you like how does the current, a simplified picture, how does the current ZK applications are verified proof today. You basically submit your proof. You write your own like a verification contract. People call it verifier.sol, and put that on Ethereum. Basically, you submit your proof. And now it's almost the same. The only difference here is that we require you to register your verification key on the NEBRA UPA contract, right? For your specific circuit, you register this key, and then you can just submit your proof together with your public input to us, and then you get a verification result, right? So everything is almost the same. Actually, one of our engineers did this experiment. He basically tried to modify Tornado Cash instead of using its native verifier, using NEBRA to see how soon he can change the code. It actually only takes 2 hours to get end-to-end working. Not just like changing the code, probably just take like 10 minutes. That's how easy using NEBRA. And we're on testnet today, and welcome to use it today, actually. So let's dive a little bit deeper on the technical part, right? The NEBRA UPA 1.0, under hood, it's a 2-layer recursion circuit using Halo 2 KZG. So there are a lot of reasons why we're using Halo 2 KZG compared with other proof system, but the TLDR here is that Halo 2 KZG might not be the best recursive proof system, but in our specific context, we need to do a lot of like non-native arithmetics, and at the time we're developing this, because it's like lookup support, and lookup is the most essential thing to support like non-native arithmetics. So this is a choice we made by then. And then under hood, to make the system efficient, we develop a pipeline and distributed prover serving architecture, which I will show you in the next slide, to having NEBRA UPA working as efficiently as possible. And then we're actually leveraging GPU accelerations to make it even faster. And this is launched about like 1.5 months ago. We have iterated 2 variants. So currently NEBRA is on UPA 1.1. Basically, we support 4 major gross-16 proof systems, like the vanilla gross-16 by Snark.js, the Gnark, and the Gnark with commitment, and also the Bellman. So these are, we almost support all the gross-16 proof systems that major developers are using. So one of the important aspects of this, why we're building this, is that essentially you can think of we're building the shared economy of proof aggregation, which essentially means more proof, the better economy. In the sense that because we're aggregating proofs from different parties, you get their shared economy with others, right? For example, the ZKTLS will get shared economy with Lagrange if there's volume from both sides, right? So the more players we're aggregating, and the better economy you get, right? So this is a great model to lower the on-chain proof verification cost for everyone. Talking to that, let's talking about some of the design choices we made when we are thinking of building NEBRA UPA. So I think one design choices we're thinking is that, so there is this argument with like building a ZK circuit versus using ZK VM. So there are several things here. First is that using a specific circuit is about 60x to 20x more efficient than VM. Because the more abstraction you add in between, the more things you're going to pay for the added abstraction layer. So it's really about trade-offs between developer time. So for example, if you want to building this proof aggregation service, how much time you are spending writing the circuit, and also the latency of the protocol, and also the prover cost. Because the circuit benefit coming from both better latency and lower prover cost. After we developed NEBRA UPA v1, what we realized that we get a lot of demand for people writing using all different kinds of proof systems. For example, and there are better and newer proof systems are developing today. For example, like I think there's a talk about Binias, right? So I think it's really kind of like proof system is this wonderful thing, and it's keep moving forward very quickly. And I do think people are developing more and better proof systems looking ahead, right? I think my favorite quote is actually from Eli Ben-Sasson. He was like, people don't really understand math. If there are more and better mathematical understanding, people probably can incorporate this kind of like an insight to a newer proof system development. And then, so basically we decided on NEBRA UPA v2, which is already working internally, actually moved to a VM plus precompile architecture, right? Which means, so we are still kind of using a ZK VM as a base layer, and then we're adding precompiles that's particularly efficient in terms of handling non-native arithmetics and this is kind of a cryptographic workload, so that it's kind of like achieving good from both worlds. And we're having like both Flunk, Honk, and Halo 2 support on NEBRA v2. So then I can cover briefly about some of the challenges of building NEBRA, right? So I think the first challenge is like, how can we handle non-native arithmetics, right? This is basically where one of the reasons like we are the first one to launch a proof aggregation service in production, is that it's actually really hard to build an efficient proof aggregation service. So the first reason is that because of the non-native arithmetics, right? Because by the nature for recursive proofs, we're actually generating proofs for proofs. And for proofs and proofs, there is a different in terms of language. So basically, for proofs of proofs, right? You want to the arithmetics you kind of embedded in the circuit is the finite field in the actual proof, which means there is like this very little disparity between these two large prime numbers, so that you need to do a lot of things to make it work. So roughly, this is equivalent to 20x blow up in terms of circuit size, compared with so-called like native arithmetics. And the second challenge here is that how can we handle heterogeneous proofs? So as I mentioned before, the key question to enable lower proof verification cost is we can have this shared economy. And this shared economy requires handling heterogeneous proofs, which means we should aggregate as wide proof as possible. So for example, for NEBRA UPA 1.0, right, we are already support 3. I guess this is a little bit outdated. We are already support 4 versions of the gross-16 with arbitrary size public input and with upper bound. And in NEBRA UPA 2.0, we're going to support gross-16 and all the other proof systems, because adding a new proof system to NEBRA UPA 2.0 is really easy. It's just like deploying the Rust developer, a Rust like verifier to our like a proof for aggregation specialized designed ZK VM. So then let's talk about a little bit about the distributed and the kind of like decentralized proving a little bit. So inside of NEBRA UPA, right, basically for a single proof batch, we kind of have this 2 layers. The first layer we call like universal batch verification circuit. You can think of where like kind of layering certain numbers of verifier circuit in their circuit. And then the green part is a catch-check circuit. It's used to handle variable lengths of catch-check. And then we generate like, say, 5 proofs, and then aggregate these 5 proofs using the aggregation circuit. By this way, right, so each individual circuit is running in an individual GPU server. And all these can run in parallel. So by this parallelization, you get like a very, very short latency. And also, we are overlapping proving over batches, which means here, so when the first batch comes, so our coordinator will actually spawn the prover cluster 1. And while the prover cluster 1 is still working, let's say at that time, there is a second batch comes. The coordinator gonna actually spawn the prover batch 2, so on and so forth. This overlapping will actually maximize the throughput as well. So as a result, right, so this is actually last December, we can aggregate 1 million proofs only over like 36 hours on Sepolia. So this is roughly like 10 proofs per second. So think about a ZK EVM proof can contain I don't know, like 1,000 transactions or more, right? So this is a huge boost to the scalability of the entire Ethereum blockchain. So far I talked about NEBRA UPA, which is the first universal proof aggregation protocol, currently already live on testnet, are gonna go into mainnet soon. So, but that's actually a fraction of our vision here, right? So NEBRA UPA is a powerful technology we built, and it's a powerful protocol, can lower the proof verification cost. But what we're gonna build next, we call NEBRA OS. It's an open stack for like a rollup interoperability. So the goal here is that we really think there are gonna be like 1 million rollups, and maybe there's one rollup running a coffee shops, and this mom and pop shop using a rollup to take people's money and issue their own coins and issue their own FTs, right? And how can we enable this kind of a future? So our view here is that there's a problem here is that I don't think the future is like 1,000 different chains. And we do think the future is 1,000 rollups, 1 million rollups, because there is essential, like the security and abstraction leakage for like cross consensus are inevitable, right? So I did a little bit talk at Research Day, so I think it's published online. Please take a look at that. I won't dive this too deep. But essentially, this is our view, right? I do think like rollups are new servers, right? So you have various kind of rollups. So you have the rollups have different kind of like a fault, how the fault is attributable. You can have like this like an objective attributable fault. You can have this intersubjective attributable fault, and you can have stateful or stateless. And you can, based on these assumptions, you can have various kind of rollups. And for all these things, right? Basically, I'm trying to convey here is that we kind of define a rollup in a general purpose way, in the sense that any kind of like stateful, verifiable servers, you can view that as a rollup. And under this framework, right? What is the best way we can bring interoperability to these rollups? I think the biggest problem of having so many rollups, and it's already there, but I think the problem will worse, is that we're actually lacking interoperabilities between different rollups. So basically, our idea here is that NEBRA, by using our proof aggregation technology, can make cross rollup transactions to be the first class citizen and to be part of settlement. This is kind of like a co-design of cross rollup transactions and settlement. Well, basically, this is a new design space we unlock, and this will bring this like native interoperabilities based on the proof aggregation technology. So for time's sake, I will just give a very high-level idea here, right? So the idea here is that, so let's say on NEBRA stack, there are various kind of rollups. Let's say rollup A, B, and C. So first, we're actually define a new transaction type called meta transaction. So basically, meta transaction here means that this is a cross rollup transaction bundle, but with some metadata. And this metadata is basically based how the constraint that how this transaction is going to set on a rollup. So for example, the most general purpose metadata could be some dependency constraints, right? Which transaction should settle first, and which is kind of a general purpose dependency graph. And a kind of a more simplified metadata could be, we call it atomic inclusion guarantee, which means these rollup transactions have to be included at the same epoch of NEBRA stack. So after this meta transaction definition, this meta transaction will send to a coordination module, and then this coordination module will ask each rollup sequencers, hey, are you wanting to include this transaction in the future epoch? If we get a confirmation from the rollup sequencer, then we actually, during the settlement, right, in addition to aggregate their validity proof, this rollup safety module will actually generate a meta transaction inclusion proofs and aggregate this meta transaction inclusion proof together with the validity proof to guarantee the safety that this meta transaction is indeed included in these epochs of settlement, in the sense that what actually brings a new communication model to the Ethereum rollups, in the sense that before NEBRA, Ethereum rollups communication model is purely asynchronous, and we're actually bringing this kind of like a partial synchrony to the rollup, Ethereum rollup stacks. And happy to chat more offline for time's sake. And with that, just a little bit benefits of what this kind of native interoperability can bring. So we actually think this is an ecosystem-wide unlock. So first, it will fix the security leakage problem. And second, it actually can have enforceable cross-rollup intent, which means in addition to proof aggregation, in addition to validity proof, in addition to the meta transaction inclusion proof, we can have rollup state predicate. And this state predicate can be, for example, hey, this trading have to be at the price lower or greater than certain price you define, for example. And also, this will bring better developer experience for chain abstractions and wallet builders. Even just having a single RPC, right, will just like solve many people's nightmare. When you do a cross-chain transaction, you need to talk to multiple RPCs, and so on and so forth. And next is that it will actually bring better capital efficiency for cross-rollup market makers. So currently, despite we have cross-rollup transactions, the market makers are actually taking the risk of the transaction doesn't go through, so on and so forth. So having a safety guarantee will actually increase the capital efficiency of a cross-rollup market maker and so on. And also, because this cross-rollup transaction is so easy, it actually decrease the liquidity requirement to start a new chain, and actually solve the liquidity bootstrap issues for many people who want to launch a new chain, and also tons of others, right? But the basic message here is that we do think the native interoperability will actually bring more friction and better UX. To conclude, today I show you two things. First is already launched on NEBRA UPA testnet. NEBRA UPA is the first universal proof aggregator. Will bring 10x more cost reduction on ZKP verification costs. And that will benefit for all the ZK projects we are here today. And second, I'll show you a little bit vision where we are building on NEBRA OS, which is bringing the native composability and native interoperability rollups using NEBRA UPA. Yeah, that's my talk. Thanks.